Today we will start with the chapter 7, part 2. We will start from section 7.3. In complex vector spaces. Okay. In section 7.3, 역시 조금 okay. Somehow 윈도우 모드로 가서 스타트. Okay. Now we start section 7.3, unitarily diagonalizable matrices. Okay. I'll choose a pencil with the blue color. Okay. On n by n matrix, on n by n matrix, on n by n matrix, A is called Hermitian, skew Hermitian, or unitary. When A is same as A star, A is called Hermitian if A is same as minus A star, and unitary if A star A is an identity matrix. Sometimes A star is called in A Hermitian or conjugate transpose of A. Okay, if those are the case of the special matrices, then eigenvalues belongs to distinct eigenvalues are mutually orthogonal. In all cases, if you have a distinct eigenvalues, then corresponding eigenvectors are mutually orthogonal. If such a matrix has n distinct eigenvalues, it is diagonalizable by a unitary matrix. This is a very strong property. Okay. The goal of this section is those matrices, Hermitian, skew Hermitian, and unitary matrices are always diagonalizable by a unitary matrix. Here is the definition. Two real matrices A and B are called orthogonally similar if there exists an orthogonal matrix P such that P inverse AP is equal to B. Okay. And a matrix is orthogonally diagonalizable if it is orthogonally similar to a diagonal matrix. If there exists a real orthogonal matrix P such that P inverse AP is equal to D. Real orthogonal matrix P such that P inverse AP is equal to a diagonal matrix. Okay? For real to real matrices. Now, in chapter 7, we start with the complex matrices. Suppose we have two complex matrices A and B, and those matrices are called unitarily similar if there exists a unitary matrix such that U star A U is equal to B. Then we call A and B are unitarily similar. If there exists if a matrix A is similar to a diagonal matrix, then we call this matrix A is unitarily diagonalizable. If there exists a unitary matrix U such that U star AU is a diagonal matrix, then we call this matrix A is unitarily diagonalizable. Diagonalizable with a unitary matrix. Okay, this is the goal, to show all such matrices are unitarily diagonalizable. Okay. Let's move. Okay. 오케이. 야, 다시 말하면 두 행렬 A, B가 에 대해서 U 스타 A, U 이퀄 B인 유니타리 행렬 U가 존재하면 A와 B는 유니타리리 시밀러하다고 하고, A가 대각선 행렬과 유니타리 닮으면 A는 유니타리리 다이어고널라이저블하다고 한다. The most important theorem on this is Schur's lemma or Schur's theorem. Every arbitrary matrix of the size n is for every matrix A, and there exists a unitary matrix U such that U star AU is a triangular matrix. Whose diagonal entries are eigenvalues of A. This is a theorem which was proved by Schur. The importance of this theorem is this theorem works for the arbitrary matrix A. So when you study or when you prove something for the given matrix A, you don't have to do all the research on A. All you have to do is to study the property of this triangular matrix, whose diagonal entries are eigenvalues of A. Okay? If you can find, if you know how to find this unitary matrix U, then you can simplify your problem or your research significantly. Okay, this theorem was proved in 1909 by Jewish mathematician Schur, who moved from Germany to Israel during the World War. Okay, here is the proof. Yeah, this is a better proof, so I will use this proof. Okay, the proof can be done by mass induction. Let's start the case when k is equal to 1, then it's a 1 by 1 matrix, then the theorem holds. It's a trivial case. So we assume the theorem is hold for the case when k is equal to n minus 1. And now we show for the case k is equal to n. Okay? This is mass induction. Okay. We start with the first eigenvalue that we can let lambda 1, lambda 2, and lambda n is a set of eigenvalues of A. Then we just give a ordering here. So let's have this ordered eigenvalues of A. Let's start with the first eigenvalue of A. Then we can find an eigenvector. For lambda 1, we can find the corresponding eigenvector y1. Then we can normalize it with this length. then let's say this one is x1. Then this x1 is also an eigenvector of A corresponding to the eigenvalue lambda 1. We call this x1 is the normalized eigenvector of A corresponding to the eigenvalue lambda 1. Okay, then we can expand this linear independent vector to a basis for Cn. Okay, so we can find the also normalized basis, including x1 for Cn. Okay, let's say this set x1, x2 up to xn is a On basis for Cn. Okay, now we have On basis including the eigenvector x1. Let's form a unitary matrix U0, U0 with whose columns are those eigenvectors, those vectors. Okay, then we can easily check the U0 star times U0 is equal to the identity matrix, which says U0 is a unitary matrix. Because, you see, think about the component of K1 entry of the matrix U0 star A U0. Then, as you see, A U0 is, and think about it. Here we have, this is a matrix U. Here we have A. Then A U0 is A x1, A x2, and A xn, like this. Okay? And here, so this is a lambda 1 x1, isn't it? Okay. Here you multiply U star. Then, if you think about the first column of this space, K1 entry of this matrix, U star times this matrix, then you will see, you will use the conjugate transpose of this case column here. So you will have xk star A times x1. This is from the 3M notation. You have seen this ij is i's row times bj's columns, isn't it? If you have A, B, C, and ij's entry, then what do you have? I's row B times Cj's column, isn't it? From here. So here you have K1 entry, then here you have K, and you have here 1 here. Okay, this 1 is the x1, the column, first column of this matrix U here, and the column, the case column of U star, U0 star is this. So you clearly have K star here and A times x1 like this. Okay. Here, so you have this. As you see here, this is a lambda x1. Since x is a scalar, so this one can come out. Then what's left is the inner product between of x1 and xk. Since this was the On basis, so this value is a Kronecker delta. If I is equal to same to j, then the value is 1. If not, then it should be 0. So you have this. The ij is on top. So since the U naught star times U naught, ij's entry of this is a Kroneker's delta. So if they are same, then they are all ones. If ij's are different, then all the others are zero, the identity. So this is a unitary matrix. And one important thing is, comes from here. You see here, the U naught star AU, the K1 entry is like this. So when K is equal to 1, we have, this is equal to 1, so we have lambda 1 here. When K is equal to 2, what happens? If K is equal to 2, then this is going to be 0. So we have 0 here. K equals 3, then this is 0, and K is equal to n, then we have 0 like this. So we have this type of block matrix. Okay? So we have a unitary matrix U naught, and the form of the shape of U naught star times A times U naught is a block matrix that looks like this. Then, see, lambda 1 is a complex matrix whose dimension is n minus 1. This is a n minus 1 by n minus 1 matrix. And what, since, and the characteristic polynomial, which is the determinant of lambda I n minus a, is same as this, isn't it? Since this matrix like this, so characteristic polynomial of A is same as characteristic polynomial of this, because characteristic polynomial, the similarity preserves the characteristic polynomial. Similar matrix have a same characteristic polynomial and same eigenvalues. This is the same. Do you remember? So think about this. Lambda minus this, let's say this is some matrix B here. Lambda I minus B, determinant of line. Then as you see here, lambda minus lambda 1 here, and here lambda I n minus 1 minus a, something like this, isn't it? Okay, so characteristic polynomial of this matrix is like this. So the eigenvalues of A1 submatrix should be lambda 2 up to lambda n, because they are same and it has root lambda 1 up to lambda n, isn't it? Here we have lambda 1 already. This should have root lambda 2 up to lambda n, isn't it? This is a very important fact. Because of that, we can use a mass induction. Okay, let's define. By mass induction, if we have a matrix whose size is n minus 1, if A1 is in here, then by the mass induction, there exists a unitary matrix U1 hat such that U1 hat star times A1 times U1 hat is this triangular matrix whose eigenvalues are lambda 2 up to lambda n. This is by mass induction. Okay? Then let's form a matrix U1, n by n matrix, like this. U1 hat is here, and all the others are 0 except 1. So it's a 1 time of U1 hat like this. Let's say this one is a matrix U1. This is a n minus 1 by n minus 1 matrix, but this is a n by n matrix. Okay. Important thing is this. With this matrix, think about this. You take, before you had U0 star A U0 here, and now you multiply U1 and U1 star here like this. Then this can be written in this way, like this. And what it should be looks like? this is like this, and as you see here, you have this is that because of direct sum. The shape of this matrix with this is just like this. Here, this is a triangular matrix, upper triangular matrix, whose diagonal entries are lambda 1, lambda 2, up to lambda n. Now you have an upper triangular matrix whose diagonal entries are all eigenvalues of A. One more important thing is this matrix, U0, U1 here. U1 was a unitary matrix, and U0 was a unitary matrix. And this U0 is a unitary matrix. U1 head is a unitary matrix, and this matrix is a direct sum of two unitary matrices. So this U1 is also unitary. So product of those two unitary matrices are also a unitary matrix. So let's say the product of U0 and U1 as a one matrix U, then this matrix U is a unitary matrix, which says U star AU is a diagonal matrix, the upper triangular matrix whose diagonal entries are all eigenvalues of A. So what you have proved was there exists a unitary matrix such that U star AU is an upper triangular matrix whose diagonal entries are eigenvalues of A. This is what Schur proved in 1909. Okay? This is Schur's theorem. This is very nice and interesting and simple proof, but also has enormous power in the theory of matrix theory. Okay. Next theorem. Any questions on Schur's lemma? Schur's theorem? Okay. Then if A is either Hermitian, then this Hermitian matrix is unitary diagonalizable. If A is a skew Hermitian, it is also a unitary diagonalizable. If A is a unitary matrix, then it is also unitarily diagonalizable. Okay, the proof is so simple because of this Schur's lemma, this theorem. Okay, by Schur's lemma, there exists a unitary matrix U such that U star AU is an upper triangular matrix. Okay, let's see. What's the B star? Conjugate Hermitian. Okay, B star is the star of this. So, this is a star AU is a star is U star, A star, and U star star. So, it is self. So, we have this. Let's see. If A is a Hermitian, then A star is A. So, if it's a Hermitian, then we have H star, U star, A, U. Then this is exactly same as B. If it's a skew Hermitian, A star is minus A. Then we have U star minus A, U, which is just minus B. If A is a skew Hermitian, we have B star is minus B. Before, if it's a Hermitian, then we have B star is B and minus B like this. What it says, if A is Hermitian, then B star is same as B. If it's skew Hermitian, then B star is minus B. Okay. Not only A. If A is Hermitian, then B is Hermitian. If A is skew Hermitian, then B is skew Hermitian. S. B, let's think about B star, conjugate transpose BH. Then this is this, and since U is a unitary matrix, it is this. Since A is a Hermitian matrix, so A conjugate transpose is A inverse, and U is itself. then this is what? This is exactly same as B inverse. Because U star AU was B, so B inverse is what? U inverse, A inverse, and U. Okay? So it's just B inverse. So B star is equal to B inverse, which says B is also unitary matrix. So if A is Hermitian, then this upper triangular matrix is also Hermitian. If A is skew Hermitian, then this similar upper triangular matrix is also a skew Hermitian. If A is a unitary matrix, then this upper triangular matrix B is also a unitary matrix. That's what it says. Let's think. Then think about the last part. Okay, as you see. Okay. Upper triangular matrix B take the same type, Hermitian, skew Hermitian, unitary as A. Okay, if A is Hermitian, then B is Hermitian. Think about this. BH is a lower triangular matrix. Okay, it's a lower triangular matrix. B inverse is an upper triangular matrix because B is an upper triangular matrix. Inverse of a triangular matrix is a triangular matrix. You remember that. Okay. Okay. So BH is a lower triangular matrix. BH is a lower triangular matrix like this. And B is an upper triangular matrix. B is an upper triangular matrix like this. If B is a Hermitian, they are same. If they are Hermitian, this should be same, isn't it? Then what's the shape of this matrix? This should be all 0. This should be all 0. What's left? Only diagonal entries. Okay? Then B should be a diagonal matrix. If A is Hermitian, then B should be a diagonal matrix. Then what do we have? This. U star AU is a diagonal matrix. A is unitarily diagonalizable. That's what we have proved. Is Lee, K. Yang, you see? Okay. Next, if A is a skew Hermitian, B star is a lower triangular matrix like this, and it is minus B is same as here. It's a triangle since B is an upper triangular matrix, so this is like this. They should be same. If they are skew Hermitian, then this should be all 0 and this should be all 0. Isn't it? So this is another diagonal matrix. So if A is a skew Hermitian matrix, then B is a skew Hermitian matrix, and it is a diagonal matrix as well. And this was a unitary matrix. So A is unitarily similar to a diagonal matrix. So it is unitarily diagonalizable. And next, and last, if B is a unitary matrix, if A is a unitary matrix, then you saw B star B is also A identity because B is a unitary matrix. Okay, then same thing. The upper triangle matrix B must be diagonal case as well, in the similar way. So U star AU are all a diagonal matrix. So there exists a unitary matrix U such that U star AU is a diagonal matrix for all three cases. So all those three cases are unitarily diagonalizable. That's what it says. Okay, so this Hermitian, skew Hermitian in unitary matrices are always unitary diagonalizable. Not only diagonalizable, it is unitary diagonalizable. The power of this unitary diagonalizable is you don't have, when you're finding the U inverse, you don't have to do it. You don't have to do any calculation. You just find the conjugate transpose. Finding the inverse matrix from a given one takes a lot of computation. But finding the conjugate transpose, it just doesn't do any calculation. Because we know all the entries, A11 and A22 and ANN. For finding this one is just print out those entries in this pattern. Then you have it. So it doesn't take any computer time to find it. So with this unitary matrix involved it, and the diagonal matrix in it, then all calculations are just not a problem at all. Whatever size of matrix you have, it doesn't matter. So it's a very powerful condition that you can use. Okay. Some more thing. If U star AU is a diagonal matrix, then as you see here, AU is a UD. Just multiply U star U on both sides. Then, as you see here, the column of U and also normal eigenvectors of A. I showed it already on this. And the diagonal entries of D are eigenvalues of A. Because A times U J's column is same as is lambda J times U at the J's column of U like this. From here, you can easily find this one. So these are the eigenvalues, and these are the non-zero vectors. And also, since this is a unitary matrix, so all of those vectors are ON vectors. So those are all also normal vectors. Each others. That's what it says. Okay. So here is some examples. The Hermitian matrix is unitary diagonalizable. The one example. So this is a Hermitian matrix. This is a unitary matrix. This is a Hermitian matrix. This is same as A star, isn't it? The conjugate of this one is A plus I, so it goes here. And conjugate of this one, which is A minus I, goes here. So just A is same as A star. So this matrix A can be diagonalized by a unitary matrix. If you find it, so you can find the two eigenvalues, distinct eigenvalues in this case. Then you can find two corresponding eigenvectors. You just normalize it, then form a matrix U such that U1 is the first column and U2 is the second column. Then this is a unitary matrix, and you will see this is eigenvalue lambda 1 and lambda 2 in the order of this. This is what it says. If you form a vector like this, then U star AU is an eigenvalue here. Lambda 1 and lambda 2 here. Here, this matrix is U1 and U2 like this. Okay. Important thing is you should have the corresponding, you should keep the order of the corresponding eigenvectors. If you switch this, then the corresponding diagonal matrix should be in this way. Okay? If you change the order of columns, then it changes the location of the diagonal entries in D. Okay. Next theorem. For any n by n real matrix, this is a special case. The following are equivalent. A is symmetric, then A is orthogonally diagonalizable. A has a full set of n also normal eigenvectors. So the way of proof is show the first sentence implies the second, and second sentence implies the third and last, and the third sentence implies the first sentence. That's the way of proving. Okay. If A is symmetric, F is symmetric, then it's a special case of the Hermitian matrix. For the real matrices, it's a unitary diagonalizable. Okay. Let's see. Real symmetric matrix has only real eigenvalues, and by Schur's theorem, it is orthogonally similar to an upper triangular matrix. By Schur's theorem, orthogonally similar. You see here, real symmetric matrix has all real eigenvalues. Okay, so here the corresponding eigenvalues are all reals and diagonalizable like this. Okay, then the first corresponding, this is a real eigenvalue and this is a real this is a real matrix and this is a real number eigenvalue. Then you are solving the linear system of Ax is equal to lambda 1x like this. This is a real and this is real. Then all of your solutions should be also real. So you have a real eigenvectors x1. Samely, real eigenvectors, and you have a real eigenvectors xn. So you have a unitary matrix whose all columns are real. So you have a unitary matrix whose entries are all real. That means U star A, U star U is equal identity because it's a unitary matrix, but this is a real matrix. What that means is U transpose U is identity. But and these are real matrices, which means that each columns are real orthogonal matrix, real orthogonal, also normal. The column vectors of this matrix U are real, also normal vectors. This all comes from the theorem that you have proved, which is called Schur's lemma, and the consequence of it. Okay? All those theorems are using Schur's lemma. That's why it can be called as a Schur's lemma. But it is also called as a Schur's theorem because it is itself a strong theorem. Okay, same thing. If A is diagonalized by the orthogonal matrix UQ, then you have a Q transpose AQ is equal to a diagonal matrix D, and the column of this matrix Q, this is a real orthogonal matrix, so these columns are eigenvectors and orthogonal, and whose lengths are all 1, so it's n orthonormal vectors. Same thing here. If A is also normal vectors, then all you have to do is just given a range of it, then form suppose you have a Q, the vector x1 and xn, then eigenvectors, O(n) eigenvectors like this, and then make it as a U or a Q, then Q, AQ is equal to QD, so Q transpose AQ is a D, so A is same as A transpose. We can show easily from this because all the eigenvalues are real, so D is same as D transpose. From here, we can easily find A is equal to A transpose, so A is symmetric. So all proofs are just well related and can be proved without any difficulty, since we have Schur's lemma. Okay, and there are some examples. Okay, team number 2, Mr. Kim, Shin, Lee. You may try on this problem number 7.17, and there are some more remarks. The procedure for orthogonal diagonalization of a symmetric matrix A. Suppose we have a symmetric matrix. Then find the basis for each eigenspace. Since it's a symmetric matrix, we can always find n orthonormal eigenvectors, isn't it? N linear independent eigenvectors. Not only linear independent, you can find orthonormal eigenvectors. So find the basis for each eigenspace of A. Then we can have a full length. The number of full, the geometric multiplicity of each eigenvalues are same as the algebraic multiplicity of eigenvalues. So we can find the exact same number of linear independent eigenvectors corresponding each eigenvalues whose algebraic multiplicity is same as the number of linear independent eigenvectors, or the dimension of eigenspaces for each of them. Then we can apply the Gram-Schmidt orthogonalization process to each of these bases for each of these eigenspaces to obtain an orthonormal basis for each eigenspace, Okay, then form a matrix Q whose columns are the basis vectors constructed in step 2, and this matrix orthogonally diagonalize A. Clearly, that's it. For a symmetric matrix, you find the eigenvalues. Then it has the algebraic multiplicities. And for each eigenvalues, you find the maximum number of linear independent eigenvectors corresponding to each of their eigenvalues. Then you will have a full same number of linear independent eigenvectors for each of the eigenvalues. For each set of eigenvalues, which is the basis for the eigenspace corresponding to each of eigenvalues. Okay. Then, since you have linear independent eigenvectors, you can adopt Gram-Schmidt orthonormalization process to have the ON basis for each of the eigenspaces. Then you have the n number of linear independent eigenvectors, and also they are all orthogonal. Because if you for the corresponding the block for the each distinct eigenvalues, you have orthonormal eigenvectors. But for those distinct eigenvalues, for the corresponding eigenvectors, the eigenvectors corresponding to the distinct eigenvalues, they are already also orthogonal. All you have to do is just normalize it. So what you have is n orthonormal eigenvectors. Since you have orthogonal, you have n orthonormal eigenvectors, so U star A Q, it should be a diagonal matrix whose eigenvalues are like this, counting multiplicity, like this. Okay. Here, since it was a real symmetric matrix, so this is same as this. Okay, like this. Okay. So this is a process that you already know it, but just rewrote it. Okay. Next. Okay. Suppose we have the matrix A like this. Then from this matrix we have this. This is a symmetric matrix, isn't it? Real symmetric matrix. We have the eigenvalue, 3 eigenvalues, 2, 2, and 8. Here, important thing is it has the eigenvalue whose algebraic multiplicity is 2. Important thing is this. We have this. We have we have the 2 linear independent eigenvectors corresponding to 1 eigenvalue lambda is equal to 2. We have 2 linear independent eigenvectors. Because it's a symmetry, it has n linear independent eigenvectors. For this, algebraic multiplicity is 2. So you have 2 linear independent eigenvectors corresponding to lambda 1 is equal to 2. And so you just adopt the Gram-Schmidt orthonormalization process on this. And then you have 2 linear independent or 2 orthonormal vectors. And then you think about the second eigenvector, lambda 2. From this one, you can find 1 linear independent eigenvectors. You just normalize it. Then name it as a U3. Then you have U1 and U2, they are orthonormal. And this is, since eigenvalues are distinct, this is orthogonal with this one, and this is orthogonal with this one. You just normalize it, then you have 3 orthonormal vectors. Since these vectors are orthonormal, the matrix whose columns are orthonormal vectors are unitary matrix or real orthogonal matrix. This is same as Q inverse. Q inverse same as Q transpose. And Q inverse AQ, which is Q transpose AQ, is same as lambda. We have U1 here, U2, which corresponding eigenvalues are 2, and U3 here, then corresponding eigenvector is 3. So Q inverse AQ is a diagonal matrix like this. Now you have a unitary matrix or a real orthogonal matrix and diagonal matrix like this. This is the way how it works. And all are guaranteed for unitary matrix or Hermitian matrix or skew Hermitian matrix or symmetric matrix or skew symmetric matrices or real orthogonal matrices. For those special matrices, you can always find this nice diagonal matrix to deal with. Okay? But here is a diagonal matrix, but this is a diagonal matrix, but neither Hermitian, neither skew Hermitian, neither unitary. This is an example of it. And there are infinitely many unitary diagonal matrices, which are neither Hermitian, skew Hermitian, nor unitary. So those 3 special type of matrices are not the only matrices which is unitary diagonalizable. There are more unitary diagonalizable matrices. That's the goal, to find what is the if and only if condition a matrix can be unitary diagonalizable. What's the if and only if condition? Here, if you have a 3 type of special matrix, then unitary diagonalizable. Good. But what about the other direction? This is a question. Okay? That's the answer. Normal matrix. Normal matrix is a complex entire matrix that holds this property. A star is same as A star A, like this. Then we call it is a normal matrix. Normal matrix. Very important matrix. This is a normal matrix. But neither Hermitian or neither skew Hermitian, neither unitary, and no diagonal. But this is a Hermitian matrix. A star A is same as A star for this one. Okay? We can find a unitary matrix that diagonalize this matrix. So this normal matrix is something. You can just easily check whether these matrices belong to one of these or not. Okay. This is. If a matrix, an upper triangular matrix is normal, then it must be a diagonal matrix. Upper triangular matrix is normal, then it is a diagonal matrix. This is a very typical proof technique. If you have upper triangular matrix that is normal, then it should be a diagonal matrix. The proof is so simple. Since it's a normal, T star is same as T star T. You compare these two matrices. If you compare that, when k is equal to 1, then you have this. Those should be same. This is same as this. So these are same. So all the others should be 0. So the first entries are all 0 except 1, 1, and 3. Second, these two, the 2 entry of this matrix is same as 2 entry of this matrix, isn't it? So compare these two matrices and KK matrix, KK entries here. Here, this is a KK entry from the right-hand side, the left-hand side, and this is a KK entry of right-hand side. These should be same, so they are same. What means is all the others should be 0, isn't it? It was upper triangular matrix, but all 0 except the diagonal entries. So T should be a diagonal matrix, because all I, K are 0 for all I is not K. It was a triangular matrix, but all of diagonal entries are 0. So it should be a diagonal matrix. With this, we can prove this one. For n by n complex matrix A, the following are equivalent. A is normal, if and only if A is unitary diagonalizable. If and only if A has a full set of n orthonormal eigenvectors. This is a key. Here, this gives us a if and only if criteria to be unitary diagonalizable. If a matrix is unitary diagonalizable, everything is so simple. When you think about the matrix A, we only have to think about the diagonal matrix. And the bridge is a unitary matrix. But unitary matrix, for the unitary matrix, we don't have to do any calculation to find the inverse of it. So there's no calculation involved here. So there's no calculation involved, but all we have to do, deal with the diagonal matrix instead of n by n matrix. So everything's are simple. This theorem gives us the final criteria to be unitarily diagonalizable. So if we can show the matrix normal, then just by checking, done. Then we know this is a very easy problem to deal with. Isn't it? The proof is similar like what we saw. By Schur's lemma, do the same thing. TTH, TT star is same as T star T. Then we can show, from the normal condition, we can show the A is unitary diagonalizable. Easy. If it is unitary diagonalizable, then clearly U star AU is a diagonal matrix. What that means is that since AU is equal to UD, each columns of this matrix are eigenvectors. But this is a unitary matrix, so all the columns are also normal eigenvectors of A. Last, if we have the n also normal eigenvectors, then just form a matrix U with that eigenvectors. Then this is a unitary matrix, and U star AU is equal to D, because AU was UD. Done. If you have n normal also normal eigenvectors, then form a matrix U, then we can easily find this one because of this. So it is unitary diagonalizable. And also from here, the A is same as U D U star. From here, we can show A star is same as A star A without any difficulty. They are normal. Done. So it's done. The others are some problems that you have to deal with. Okay. Then section, the main part of chapter 7 are all covered. The last section in chapter 5 is some applications of the facts that you have learned. Okay. I think that's it. Any questions on chapter 7? Any questions?